we build a simple molecule like ethane, C2H6. We've got a carbon-to-carbon single bond. We might expect the molecule to inhabit any one of all possible conformations with that carbon-to-carbon bond giving us free rotation. There's one very specific kind of rotation, one very specific shape to the molecule, which almost always holds true. It's because of the interactions from bonding orbitals around the surrounding atoms. So we need to draw something that we refer to as Newman projections. And a Newman projection is what we imagine to see when we look along a very particular carbon-to-carbon bond. In this case, the carbon-to-carbon bond in ethane, in this example. As we look along the side of the molecule, so that the two carbons are actually eclipsed on top of each other, we draw a Newman projection which shows the sprouting carbon-to-hydrogen bonds around those two carbons. For the carbon in front, this carbon here, as this is the direction in which we're looking, the three hydrogens which are attached, we show their bond to this front carbon, we show it as lines coming from the center of the circle, projecting out in this tetrahedral manner. And for the hydrogens which are attached to the second carbon, which are the closest eclipse behind the first one, the bonds to the second carbon, we show those lines being stunted and stopping at the edge of the circle. Because of course we can't see the rest of the bond any more clearly. Okay? So this is how Newman projection builds up. So we use the orange to represent the red on the paper here, and I want to use the green and blue. We're looking at this molecule side on, so your eyes coming from this side. Looking at it side on, as you look at the molecule, and your hydrogen to carbon bonds, they spray out in a tetrahedral fashion. These two dimensions, it looks as if they're taking up a Y shape. Three bonds at the front, and then three bonds slightly at a different angle and at the back. Okay? That make sense? Mm-hmm. Okay. So these are the Newman projections. With this carbon-to-carbon single bond, you would expect free rotation around that carbon-to-carbon single bond. You would expect the molecule to be able to take any conformation. Okay? In theory, that's what should happen. Any possible conformation. What we find is that not all conformations are equal in terms of their energy to hold that particular conformation. And there's two extremes, the highest and obviously the lowest conformations. And molecules are like people. They're lazy, they want to expend as little energy as possible. So why stand up when you can lean against the bench? Why lean against the bench when you could sit in the chair? Why sit in the chair when you could lie in a comfy bed? You'll take the most comfortable conformation, the one that expends the least amount of energy. So there's two extremes we can look at. We can look at the highest and the lowest possible conformations. So as we're looking along that carbon-to-carbon bond, with the second carbon eclipsed behind the first, of course, the lowest conformation possible is when the chemical bonds are staggered to each other from one carbon atom to the next. The bonds are staggered 60 degrees at a time. Okay? So there's a carbon to hydrogen bond on the first carbon, and nearby on each side, its nearest neighbours are carbon to hydrogen bonds on the second carbon. This gives us the lowest energy conformation possible. Compared to the eclipse conformation, and we have just slightly separated it, and we're saying that each of these carbon to hydrogen bonds is directly aligned over the top of each other, albeit on either the first or second carbon. And we find that this increases the energy of the molecule increases the energy by a whopping 12 kilojoules per mole in difference. And what it's telling us is that these chemical bonds and the bonding electrons in those bonds, which are from negatively charged pairs of electrons, the electrons in those bonds are too close to each other for comfort. They're causing forces of repulsion. And for every pair of carbon to hydrogen bonds, which are eclipsed in this way behind each other, it causes 4 kilojoules per mole of strain energy in the molecule. 3 times over, it therefore gives us a total of 12 kilojoules per mole of strain energy. So, most of the time, the vast majority of the molecules are going to stay pretty close to this staggered conformation because it's lower in energy. And molecules always look for the path of least resistance and the lowest energy. So the staggered conformation is a conformation like that. And then our eclipsed conformation is like that, where they're actually aligned on top of each other. And it puts chemical bonds, bonding pairs of electrons, too close for comfort, to adjacent bonding pairs of electrons. It causes a strain or repulsion energy. So, that's our first kind of strain energy. A carbon to hydrogen bond on one carbon are lined up or eclipsed with a carbon to hydrogen bond on the second carbon. This causes what we call torsional strain, and it's about 4 kilojoules per mole of strain. So let's look at the torsional strain for a molecule like propane. Feel free to build the propane molecule up so you can look at it yourself in the same light to give yourself a better idea. So now I'm looking at a molecule of propane, and again looking down the carbon 1, the carbon 2 bond in the molecule, and looking at the two extremes of conformation. And this time the difference between the two conformations has increased in strain energy. The last example was just 12 kilojoules per mole strain energy, but with the carbon to carbon bond in propane, it's actually increased to 14 kilojoules per mole. It's because we have a new kind of strain between bonding pairs of electrons. So our low energy here, staggered, keeps those bonding pairs of electrons sufficiently apart to avoid any strain. But when we eclipse the molecule up, we see, as we saw before, that CH to CH torsional strain, which is 4 kilojoules per mole, and a second CH to CH torsional strain to give us 8. And then the last one is a carbon to hydrogen bond aligned up with a carbon to carbon bond with 3 hydrogens attached, which we'll surmise as being an H to CH strain in the notes. Because of those hydrogens which are projecting off the carbon, we get a little bit more strain energy. This time it goes up to 6 kilojoules per mole. It increases the strain energy of the molecule when it's in its eclipsed conformation, increases the strain energy up to 14 kilojoules per mole. Again, it's these bonding orbitals between the carbon to hydrogen bond and the carbon to carbon bond, which are too close together, causing repulsion, causing us torsional strain, as we know. Don't forget, when you're building your models, you're using the shorter stems for carbon to carbon single bonds. The longer stems are used in pairs for the carbon-to-carbon double bonds. So there's our second kind of strain energy. Remember, these are strain energies just for molecules which are in an eclipsed conformation. There's no problem yet with the molecules and the bonds when there's a staggered conformation. This is just eclipsed torsional strain. Carbons bonded to hydrogens, which are eclipsed, gives us 4 kilojoules per mole each time. And carbons attached to a hydrogen or another CH3 group, when those groups are eclipsed behind each other, then we go up to 6 kilojoules per mole. Let's look at a molecule like butane and look along the carbon-2 to carbon free bond and look at the strain energy involved in the molecule at that point. Then again, depends upon whether we're talking about a molecule with eclipsed or staggered conformations. Now it's a bit more complicated as it undulates back and forth. We've now got 1, 2, 3, 4 energy levels possible as that carbon-2 to carbon-3 bond rotates around. We've got along the molecule, we've got CH to CH strains, which we've already seen, which is 4 kilojoules per mole. We've got, again, it's using these red and blue dots to represent the front and back methyl groups. We've got the CH to CCH3 groups, which we said was 6 kilojoules per mole. We also have a third kind of strain energy we need to look at. Updating our table of strain energies again. We've got the H2H, which is 4, H2CH3, eclipsed, which is 6. And then we have a situation in the eclipse conformation where it's a CH3 group attached to the carbon, eclipsed behind another CH3 group on the second carbon. And this causes a whopping 11 kilojoules per mole of strain energy. Again, feel free to build the butane molecule to show that. So we're aligning the molecule up into the eclipse conformation and looking along that carbon-2 to carbon-3 bond. And looking along that bond in an eclipse conformation when the first CH3 group and the fourth CH3 group are eclipsed behind each other. So the molecule looking like that, okay? As a look to the side, there's much more strain energy going on here. We've got the 4 kilojoules for the hydrogen eclipsing. And we also have a CH3 group eclipsed behind another CH3 group. And this is involving much more strain energy. Not just from the bonding pairs of electrons, but we also have, if you look at the CH3 groups, look how close the hydrogens when those CH3 groups are to each other. You can actually make the model touch. You can make them touch each other as you rotate those CH3 groups around. So it's not just bonding orbital strain here, there's also a physical presence of the atoms almost on top of each other. This is what we refer to as sterical strain. Positively charged protons in one nucleus getting too close to positively charged protons in another nucleus. The atoms are virtually trying to occupy the same space, or at least getting too close to comfort for that. So we've been talking about torsional strain, which is bonding orbitals getting too close. When the atoms themselves are physically getting too close to each other, that's when we talk about sterical strain. And that CH3 group interaction in this eclipse conformation is a mixture of the two. Steric from the bonding orbitals and torsional from the atoms themselves, giving 11 kilojoules per mole of strain. As we move that molecule around, it also gives us a fourth kind of strain energy in the molecule. Something that we call the gauche strain. And it's our one example so far of a strain even when the molecule is in a staggered conformation. And it's when we get two methyl groups on the molecule which are staggered by 60 degrees to each other. And those CH3 groups are still too big and too close for comfort. I'll show on this molecule here. There's the molecule in the eclipse conformation. If we stagger it by rotating around just 60 degrees, this CH3 group at the back and this CH3 group on the front carbon, they're still too close to each other. And despite the staggering, it still causes some strain energy, causing 3.8 kilojoules per mole of strain energy. So to get this molecule through its carbon-2 to carbon-3 bond, to get it to its lowest energy conformation, we're going to have to rotate the molecule once more. Rotate it until those methyl groups are safely away from each other. There it is, staggering of 60 degrees. We rotate around again. So now the two groups, there's our carbon-2 to carbon-3 bond that we've been looking at. And now the first and last methyl groups are actually staggered 180 degrees from each other. There's our Newman projection again. And now, through that carbon-2 to carbon-3 bond, they're now completely on opposite planes of the molecule, 180 degrees to each other. Now we've got them far enough from each other to remove all torsional strain. And this gives us the lowest energy conformation for the butane molecule. Everybody's getting out of everybody's way. But when we look at that molecule side on, notice how, as we go down the chain, that causes the molecule and its backbone to actually zigzag back and forth on itself. This is why when we draw line-angle formulas for molecules, we tend to see these zigzags of the carbon-carbon chain, because it actually naturally gives us the lowest energy conformation for the molecule, cutting out all torsional strain and cutting out all sterical strain for the molecule.